Okay, so it is time to begin discussion. We have very sparse group today, but basically just want to get a sense of how you guys are finding the class so far. Any questions before we start? Cool. All right. How's Risk 5 coming along for you guys, understanding it?
It's going all right.
Okay.
Re-remembering things.
Uh, most of you, I guess, have taken 61C.
I feel like everyone has, right?
Okay. A couple people haven't.
Oh, really?
So
Huh.
yeah. Okay. How's homework 4 treating you guys? I'm just checking. All right. Yeah. Start immediately because it is pretty long. Yeah. And as for midterm prep, so make sure for homework 4 you do the midterm prep stuff, because we want to make sure that you guys are all set up for midterm, you know, logistics before, having to do that. Okay. So yeah, you guys are lively in the chat. So with that, I guess I'll get started. All right. Okay, everyone can see my screen, right? Yes, yes. Okay, awesome. So today we are going to dive into more detail about risk 5, obviously. And the point of this discussion this week is to sort of emphasize a couple points that you guys would need to sort of succeed in the homework and this midterm. Because the lecture slides are very good in terms of telling you what exists and how the data path is exercised. However, you guys need to sort of understand beyond that, about some of the design choices behind why risk 5 is the way it is, and also how um, all the different parts in the data path in the control logic interact with each other, and even more so like how they currently don't interact with each other and could interact with each other, so that you can enable custom instructions that you want to accelerate certain tasks. Okay, so for example, like in the homework, there are two tasks that we want to try to accelerate using the existing framework. One would be some simple ReLU function, and another one would be sort of a bitwise multiply accumulate. And for both of those problems, you need to sort of understand, how can I use like one part of the data path to influence another part of the data path? Or how can I modify one part of the data path in order to do the calculation that I need to do? Okay. All right, so basically, just to hammer home some RV32I design choices, recall that this ISA is a so-called load store ISA. And what this means is that, all of your ALU operations are done on registers or immediates, but none of it is done in data on the memory that is, sorry, none of it is done on the data that is in the data memory. So if you want to access anything or put anything to the data memory, you must use load and store operations, okay? All right. Then the next part is that the decoding in this ISA is designed for maximum hardware efficiency. So what do I mean by this, right? The most basic thing is fixed length 32-bit instructions, okay? And so when you have fixed 32-bit instructions, as opposed to some other ISAs which have variable length instructions, what does that afford you? Anyone want to, give a guess? Anyone have an idea why all instructions are 32 bits? Okay. Basically, if you have fixed 32-bit instructions, it's easy to decode because you know exactly the bit positions of everything for each particular type of instruction, and you don't need to shuffle bits around just to get to what you need to do. So it trades off a little bit of, storage that is required to run or to store your assembly program for the efficiency in the hardware that decodes it. Okay. Anyone know off the top of their head which 9 bits in the instruction actually encode instructions?
The first opcode and function.
So I said opcode and function. So opcode, which bits are opcode?
Which section is opcode?
Yeah.
From 0 to 6.
Correct. Okay. All right. What else is there?
And function is at 6 to 6. Oh, wait a second. I'm out.
Okay. All right. So it's actually not even 6 to 0. It's actually 6 to 2, because in RV32I, bits 1 to 0 always equals 1, 1. Okay. And the other bits that are in this are actually bits 30 and 14 to 12. So I believe this is funct 3. So with the combination of these 9 bits, you are able to encode the intention for every single instruction in RV32I. Okay. So really, like this instruction, ISA in this particular base set is really just a 9-bit instruction set. And then all the other bits are encoding the data, which is such as the registers and the immediates. All right, so the locations of all the fields, let's say RS1, RS2, and RD, they're always in the same position. Why does that help? Someone take a guess?
You don't need a mux to decide whether source, the register source, and it saves states and power.
Correct, absolutely. Okay, this is a little more advanced. So the immediates, if you notice, like in these two, S-type, B-type, the immediates are always packed to the left, as in you'll always see, the immediate start from bit 31. Why is this done this way?
Don't you always have a part of the circuit that always treats the leftmost part as immediate, and it muxes it at the end?
Yes, but why particularly are immediates packed to the left? Like, why doesn't immediate start somewhere here? Okay, yeah, I think Max basically answered it in the chat. It is to facilitate sign extension. So you always know that the sign bit of the immediate is going to be in bit 31, right? So you're just going to take bit 31 from the instruction, and then you're going to sign extend by copying however many zeros you need to fill the rest of the immediate. Okay?
Quick question.
Yeah.
Why does that inherently make it easier? Like, what if you always had like, bit 21 as like the end of the immediate? Then couldn't you always just take that bit and you achieve the same thing?
In some respects, yes. But once you start having to deal with all the other ways of encoding the instructions, it becomes easiest to just have the MSB always be your signed bit when you're interpreting the source number.
Okay.
Yeah, because that gets a direct translation to bit position 31, and then however many bits you need to sign extend just depends on the instruction type. Whereas instead of like taking bit 21 and then moving it over to 31 and then sort of deciding where the rest of the bits need to be. So it just saves a little bit of logic. Okay, and then B and J types have sort of like a bit rotation. So if you notice, like, immediate here and immediate here, right? This is 12, 10 to 5 instead of 11 to 5, and here's 4 to 1, 11. So why do you think that they did this?
That seems like the last bit of the B type is not necessary. That's why we can disregard it.
Correct.
So we can have extra bit to represent like more numbers.
Right. Okay. So you are correct in that the 0th bit of the immediate doesn't matter for branching, right?
I'm not sure why.
Okay. So the reason why it's covered in the lecture slides, but when you branch, right, you're branching to a instruction, target instruction, and instructions in RV32I are in multiples of 32 bits, right? And 32 bits is equivalent to 4 bytes. Okay, so theoretically, the last 2 bits don't matter because your instruction should be in multiples of 4 bytes. However, there is a extension to RISC-V, which allows for 16-bit instructions. And those 16-bit instructions are 2 bytes. So therefore, the branch target, the offset, has to be in multiples of 2 bytes. And multiples of 2 bytes means that you can discard only the 0th bit. Okay, so that's the reason why the 0th bit is discarded. Now, the reason for why like bit 11 comes to here is because, again, to simplify logic, right? Bits 4 to 1 stay in the same position. Bits 10 to 5 stay in the same position. So you only need to figure out, the difference between bit 11 in B type here and bit 11 here in S type. And that's really, that simplifies, again, the decoding logic. All right. Okay. Also to emphasize, RV32I is basically sort of the base instruction set, which is a set of 37 instructions that are enough to run any C program and consists of these types of instructions. However, you will see in assembly, RISC-V assemblies, there are also additional pseudo instructions, right? So some pseudo instructions could be like LI, which is load immediate, J, which is a unconditional jump where you don't even need to keep the PC+4. There's also like, move, like MV, which is to copy a register. So these are all implementable with combinations of other base instructions. But having these instructions makes it sometimes clearer in assembly what the intent of that instruction is. And then some of the stuff is this reserved opcodes for ISA extensions. So you'll see on this table that there are some opcodes that are already allocated for like 64-bit extensions, 128-bit instructions, floating point, stuff like that. But there are also a couple like reserved ones, like custom, you'll see custom 0, 1, 2, 3. And those are very useful if you decide that you want to add some instructions to the ISA and have enough instructions that warrants a whole different set of opcodes. Okay, so you can refer to some of the 61C materials if you really want to get in depth. But for the most part, what's covered in lecture and discussion is sufficient for homework in return. All right, so now moving on. Basically, when you approach RISC-V for homework and midterm, you really need to understand it from the instructions forward. So you need to really understand why the instructions are encoded the way they are, then understand, how the data path grabs those instructions and packages them in a way that is useful, right? So the first type is arithmetic instructions, right? There's going to be R-type and I-type arithmetic instructions. So can someone tell me basically how many distinct modes the ALU has when it comes to arithmetic instructions? Anyone want to list out what the ALU can do, basically? Throw some words out there. Okay, so shift, right? How many shifts are there? There are multiple shifts, right? You have a, SRA, so, right? SSRL, what's that? Oh,
I keep mistyping it, but you know what I mean.
SRL,
Sorry.
okay, right.
Yeah.
So this is a shift left logical, shift right arithmetic, and shift right logical. Okay, so you have shifts. What else do you have? Okay, add, right, sub. Okay, what else? And, right? Or, XOR, okay. And what else? No, mul is part of the M extension for multiply. So mul is not one. What else is there? You're missing 2 more. Okay, this one is less used, but set less than, yeah, there you go. And SLTU, set less than, unsigned. Okay, so basically this comes out to about 10. And that's how many distinct modes ALU has. Okay, so what's the difference between set less than and set less than unsigned? Right?
I have questions.
Yeah.
Do we need to memorize those for the exam or not?
No,
really?
this actually happens to be a homework problem.
Oh, okay.
Yeah. But I mean, like when it comes to doing your projects, you're gonna have to implement it, right? So yeah.
Like
okay.
we don't have to memorize that for the exam, right?
No, you don't. You can work it out yourself based on, the instructions that are in the base instruction set. Yeah. Right. So like the R type is going to be register, register, and the I type is going to be register immediate, and they both use the same set of instructions. for the ALU specifically.
Wait,
All right, so
what are the M-type extensions for the IC?
M-type extensions are things that calculate multiplication, division, and remainders.
Okay, so they're not part of the base ISA?
They're not part of the base ISA. Right. Okay. Yeah, because you can implement a multiplication without a multiplier. At the end of the day, it's just doing some shifting and XORings and ANDs and additions, right? Okay, so what's the difference between set less than and set less than unsigned? Yes, so set less than compares a signed number, but more specifically, it interprets the second register, even if it has like a bit in the MSB, as an unsigned number. Okay, and then SRL and SRA, what's the difference? So SRA is arithmetic shift, and what is that? What do you need to do when you do arithmetic shift?
Sign extend.
Right, perfect. Okay, so question, why is there a SLT but not a SGE? So you're saying like set greater than equal? Because SGE is just the opposite of SLT. So if you want to do that, you just swap the registers going in.
Wait, but by that logic, why do we have a branch greater than equal to?
So branching is different, right? Branching is you are comparing two registers and then telling the PC to update. So that's more of like a control thing, the branch comparative. However, set less than is just saying, oh, it's a 1 if it's less than, it's a 0 otherwise. That's all.
Okay.
Could you elaborate on SLT? So you would have, no, SLT is you treat both as signed numbers, and SLTU you treat both as unsigned numbers. But you don't like turn any of the numbers from signed to unsigned representation. Like, that doesn't exist because there's no logic that would enable that. So you just take the bits directly as unsigned or signed. That's the difference.
Question?
Yeah.
So can you give an example on how the ALU like does the SLT? Like if we have two numbers, what does the ALU does?
So it's sort of like essentially like the output would be sort of like a sign RS1 less than RS2.
Okay. So it's either like 0 or 1.
Yeah.
Right? Yeah. Okay. Thanks.
Okay. So when you have the next set of instructions are going to be load store. Okay. And loads are I type and stores are S type. Generally, you are addressing by a byte, right? Similar to your instructions. And you want to address the memory in little endian form. Okay, so what is the largest memory address that you can load or store to based on this and this? Does someone have an idea? Okay. How did you get that? How did you get 4 kilobyte bits? Or is it bits or bytes that you're talking about? Okay. 2 byte. Okay, not quite. It's actually, if you notice, the S type doesn't have a 2-byte offset, right? It actually goes all the way to this. Yes. So Max says it's a 12-bit immediate, right? Right. This encodes basically plus minus 2 to the 11th offset from a source register, right? And how many of this is this? This is 5 bits. So you can calculate what is the largest memory address that you can actually execute or access. Now, the question is, based on the data memory that you have in your core, might this address actually be accessible? Not necessarily, because your data memory might be smaller than this largest memory address. Okay, what happens if you overflow right? So in the case you specify a address that is larger than memory, what would happen? This actually ends up being implementation specific, but most of the time you would just like wrap around. Okay. When it comes to store, what's the difference between W, H, and B?
SW is store word, store half word, and store byte.
All right, so what's the difference? So word is how many bits?
It's 4 bytes, so 32 bits.
Okay, 4 bytes, 32 bits. Half is?
2 bytes, and byte is 1.
Right, okay. Byte equals 8 bits. Cool. Now, what is this now? U. When you do a load.
So that tells you whether to sign extend or not when you're loading into a register.
Right. So
32-bit
U
register
equals essentially fill with zeros. And then otherwise sign extend, right, to 32 bits. Awesome.
What was that here? Is that UI fill? What was that equal to fill?
Sorry. Fill with zeros.
Oh, so it's U?
Yeah, so U means unsigned.
Okay, unsigned, okay.
Which means fill with zeros. Okay. Cool. All right, so these are sort of the assembly instructions that would encode these types, as you would see in assembly code. So that's just the general format that you would see it in. Okay, now we move on to conditional branches. So this is a very important one. B-type instructions are very similar to S-type. Why and what's different between the two? So I kind of alluded to this before. Right, so we said that B-type discards bit 0, right? So that's one difference. But why don't we just make branch instructions S-type? Yeah, okay, correct. So they're similar because there's no RD, no destination register, and yes, what's different is that B-type has essentially a 13-bit immediate that it can use. So by doing that, you can extend the reach of your branch by 2x compared to a store. Cool. So when you do branches, how many comparator units are in the branch comparator? Like how many comparisons are actually being made? Yes, which 3? Okay. What else? Not quite. So branch greater than or equal to is actually just not branch less than. So the 3 is actually branch less than unsigned, branch less than, and branch equal. Those are the only 3 comparisons that are being made inside the branch comparator. You can derive all of the other branch instructions from one of these 3 outputs. Okay. And then one of the things that is very important later on in this course, when you start learning about pipelining, is how to resolve branches when you have pipeline. So what's going to happen is like, you don't know if you're going to take the branch until you actually execute it, right? And if you take the branch, then the instructions that come in the pipeline afterwards become invalid or something. So you might need to flush it, you might need to predict or stall the pipeline. There's many other things that happen. So these are some things to think about after the midterm. Okay, next type of instruction are jump.
Sorry, so can I ask a question? So for B-type and S-type, they have different immediate because they are different byte addresses. B-type is 2 byte addresses. And
yes, so
S-type
B-type
is byte
has
address.
multiples of 2 bytes, yes, because we said it doesn't need to address at the byte level.
So S-type should address the byte level.
S-type needs to address at the byte level.
I thought it's a half words or over words. Right?
No, recall you can address by byte, store and load by byte.
Okay, I got it. Thank you.
Okay. All right. Next is jump. So you have jump and link, which is a J-type instruction versus jump and link register, which is actually an I-type instruction. So what is the range of these two? Okay, so I'll just sort of give it to you in the interest of time. Jump and link, notice you have 21 bits immediate, right? So therefore, the range of this is going to be plus minus about 1 megabyte. Whereas jump and link register only has 12-bit immediate. And I think this comes out to plus minus 2/11, which is 2 kilobyte. Okay, so when would you use jump and link versus jump and link register if they have different reach? Okay, it turns out that jump and link register is very useful for accessing even bigger ranges than you can do with jump and link. And because they are often used with other instructions such as load upper immediate and AUIPC. So you can go through the spec to see what these do and how they interact with each other. And for both jumps, they will always write PC+4 to the destination register that you specify, unless the destination register is X0, which cannot be written to. Okay, and then finally, these two, load upper immediate AUIPC, are so-called upper immediate instructions. They are U-type, and the key is that they get the upper 20 bits of an immediate into the destination register. And if you want the current PC, you can use AUIPC with immediate equals 0. Question, what does jump and link register use R1 for? That is the base on which you apply the offset, which is the immediate. Yeah. Cool. All right. So yeah, here we have a couple more, ways of how you would write the assembly for these 3 instruction types. Okay. So with that over, we're gonna just talk about the data path and the control now. And what I want to emphasize is that for this discussion, we're going to go over 2 sort of more important or tricky parts, which are going to be the immediate generation and the control logic. Because all of the other stuff is pretty straightforward, right? It's pretty straightforward that the program counter, selects an address, and that gives you an instruction coming out from the instruction memory, right? The other thing is the register file, which is just 32 times of 32-bit register, right? So the register file is pretty straightforward. You can write to it, and you can read 2 registers out at the same time. The branch comparator, as we already discussed, just compares the 3 types, right? Branch less than, unsigned, or branch equals, and then that outputs here, right, to the control logic. The ALU already we went over. This has the 10 modes, right? The data memory stores the data, very similar to the instruction memory, except that the address is coming from the ALU. And then all the other stuff, right? These are like muxes and muxes. So these all come from the instruction, or from the control logic to route all the data around, okay? So data path really, we should go over 2 parts, which are the immediate generation and the control logic. Okay, so let's start with the immediate decoding. Basically, this big table on the bottom shows you which bits of the instruction ends up in the generated 32-bit immediate, right? And so you can see that, we discussed earlier, instruction bit 31 is always going to be over here on the left. So it's easy to put that there and then copy however many you need. And then you just grab the rest of the instruction bits and fill in according to the instruction type, okay? Generally, how this is implemented is that the immediate generation constructs all the types at once, and then you just mux out which type that you need based on immediate select that is generated from the control logic. And yeah, basically, when you look at the immediates that are generated, you want to pay attention to sign extension and filling of 0 here, here, and here. Okay. All right. Then the next part is the control logic, and basically you want to emphasize what are the inputs and what are the outputs, and what inputs influence which outputs. Okay. So instruction obviously is the 32 bits of the instruction from the instruction memory, right? This is used by the control logic to control everything, right? The other two inputs that you have are the branch equals and branch less than from the branch comparator up here, right? So branch equals obviously is if the two are equal, less than is if one is less than the input 2 of the comparator. Now, what do these influence, right? This is one very important thing. It influences the PC select. And why is this? Because when you branch, if you take a branch, then you grab the ALU output, right? This is taken. And if it's the branch is not taken, then you select PC plus 4. Okay. Immediate select, we discussed on the previous slide. You select one of 5 types. The reg write enable enables write back to the reg file. BR un is just telling the branch comparator to be in unsigned mode, which executes this one instead. And then A and B select are the two muxes that give the proper inputs to the ALU, right? You can either have PC or register 1, and then the other input would be immediate or register 2, and those are your only options. One of the things that may be important or may be useful is to sort of think about how the A and B select muxes can be expanded so that you can use the ALU with additional types of inputs or different combinations of inputs. Okay, like let's say, what if you want to do PC and the immediate, right? Or sorry, have another register or another immediate coming to the ALU. Okay, and then ALU select, yes.
I have a question. So you're saying that this ALU can also, like, since I only have doing very few operation, we can just assign more operation to this ALU.
Yeah. So when you think about how to extend the instruction set, yeah, you can think about, okay, so I only have 10 modes in the ALU. What if I added something else to the ALU? What can I do with it, right? Do I require different inputs?
But the ALUs for the PC select, it's only, I think that's doing less work than the ALU.
Correct.
For the,
Yeah, the ALU for PC select only does PC plus 4. That's the only thing.
So that one we can maybe assign more text to it for the additional instruction, right?
Yeah, okay. Yeah, right. So like, for example, one of the things, extensions to the ISA is a 16-bit instruction, right? So when you have a 16-bit instruction, how much do you increment the PC by? Is it 4? No, right? You increment the PC by 2 bytes instead of 4 bytes. So once you start adding these extensions, that ALU for the PC gets more complicated. Okay. Yeah, and the last two outputs from the control logic are memory read-write, very straightforward, telling data memory whether it's in read or write mode, and then write back select, which tells the register file whether the destination data comes from the data memory, the ALU, or PC plus 4. Okay. So the key takeaway here is that the only real input to output influence is the branch comparator to the PC. And another very ripe field of possibilities that you can do when you expand this ISA is to use the branch comparator for some of the other outputs, or interpret some of the inputs a different way, or get another input to the control logic to do something else. Okay. Can you say the part about PC plus 4 not being true under RV64? Okay. So PC plus 4, right? This means that you're jumping 32 bits every time, which implies that you have 32-bit instructions, right? So if you have RV64, your instructions are 64 bits, right? So you're gonna have to do a PC plus 8. If you have RV16, well, it's not really a RV16, but it's technically, oops, what did I do? It's actually RV32C, which is compressed, then you would do PC plus 2.
But isn't the JAL instruction always 4 bytes? So wouldn't you always just go to the instruction after the JAL?
Yeah, so JAL instructions are not really, I mean, JAL, you provide a label, which is sort of a direct encoding of an instruction address. So you just have to make sure that when you write this, the label is encoded properly.
Yeah, but aren't we talking about the not taken PC+4 case?
Oh yeah, the not taken.
In that case, I thought it would always be PC+4 because the JAL instruction is 4 bytes.
JAL. No,
like
we're doing this. We're talking about branching, right? Oh, I see what you mean. Yeah, I think you're right in that. Yeah, I think you might be right. I'll have to check, but I think you're right in that RB64, the branch instruction is still a 32-bit instruction. Yeah.
Okay.
Yeah, you might be right. Okay, so PC+8 might not exist. Okay. Yeah. So what I want to do for the remaining part of this discussion is I want to break you guys up into breakout rooms. And essentially what I want to do is have, sorry, how many people are there? Okay, there are 10 of you, right? Okay, so I'm gonna make 5 breakout rooms. And what I want to do is let's gather a set of 5 instructions that we want to work out, okay? Like what I mean is like you say, okay, I want to work out how the add instruction makes its way through the data path. Okay, so what I want to do is people just throw out instructions that you want worked out. Okay, just put it in the chat, and then each breakout room will do a different instruction, and then we'll come back. Okay, so one would be load bird. Okay, what else do people want to do? Okay, store byte. What else? Okay. Branch less than. What else? Okay, jump and link. And AUI PC. Cool. These are hard ones. Okay, so I'm going to break you guys out into breakout rooms. And I'm going to give you guys 5 minutes to work it out between the 2 of you in the breakout rooms. And then when we come back, I want you guys to describe what you got. And then we'll just work out each of those problems, okay? Actually, I'm going to do this 4 minutes, just in the interest of time.
So the control logic, you mean, is what you want us to figure out? Like what bits?
No, I want you to like essentially, highlight every path that is executed or exercised for each of these instructions. Okay. All right. So I'm going to open and see you guys in 4 minutes. So, yeah. Okay, is everyone back?
Yeah.
Okay, so group one. Oh, I guess it's only Lisa. Tell me, what is in load word?
This is just the control logic, right?
Well,
Or
give me as much as you can about what is exercised in this whole data path.
oh,
load word.
okay. Well, the PC goes +4 because you just move straight to the next instruction. After
Okay.
this,
So-
you
Oops, sorry. So PC +4, right?
yeah,
Okay.
and then for the immediate select mux, you select the one from the I type.
Okay. Cool.
And
Alright.
then
This
for
right
the
here.
A select, you select from the register.
Cool. Oops.
And then for
Yeah,
the
that
B
was right.
select, you select from the immediate,
Awesome.
and then you add, and then you read from memory,
Okay.
and then you enable reg, or the reg write, enable that, and then your write back select is from memory.
Cool. Perfect. Great. Yeah, that's pretty much it. Very good. Okay. Group number 2. You guys are, what is it? Store bytes,
was-
right? Okay. So tell me what's executed.
Well, for starters, we go to PC +4. So
Okay.
PC select is PC +4.
3 + 4, right?
And then for A select, we're going to choose RS1.
Plus
That's
1.
the
okay,
address to store to.
Cool.
Does my partner want to chime in?
Yeah, feel free.
The immediate select is S.
Okay, so immediate is selected. And which one? S. You said?
S.
Awesome. What else?
And
Uh,
register
data-
right enable
Mhm.
0.
I didn't hear that.
Do not write to register file.
Do not write. Okay, so this is 0. Okay.
I
Oh,
mean,
he said reg file.
Oh, do not write to reg file. Okay. So no write back. Okay, so this is 0.
And then write to data write is, or memory write is write.
Okay, so this is a write. Okay. All right. What else? That's it, right?
Yeah, I think so.
Okay. So right. So this is a don't care.
Yeah, rest or don't cares.
Awesome. Yeah, I believe that's correct. Okay. Third, what is the instruction that you did?
So I think I can go first.
What was the instruction again?
It was
The
BL2.
instruction
Oh,
B
BLT.
branch less than, yes.
Okay. All right. Go for it.
So we may access the red RS1 and RS2
RS1 and
and
RS.
get the data out. Yes,
Okay.
and
Cool. Right.
and no, to go to the branch comparator.
Yeah. As in the branch comparator is executed, and it is going to
Yes. And
give you
we will
this.
have the B select signals choose 1 to get the PC value and immediate value for the ALU to
Oh, got
get
it.
value.
I see. Okay. So I drew this wrong. Yes, you are right in that. Yeah, you actually use the immediate.
And the immediate type is B type, right?
Okay. Cool.
So we have big select 1 and we get the address out.
Yes.
And it will go back to the PC select.
Okay. So this comes back to here, right?
And we will
then-
choose from PC +4 or ALU
So
results.
this is going to be taken or not, right?
Yes,
Great.
I think that's it.
Yeah, I believe that's it.
Yep.
Great. Okay. Next one. Group 4. What was your instruction?
Sorry, was that Dylan? Was that group 4?
Yes.
I forgot. Okay, cool. I guess we can do maybe AOE PC,
Is that
or
okay.
I don't remember. What do you mean? Like, which was our instruction? I'm sorry, I don't remember.
Which one was the instruction assigned to your group?
I'm sorry, I don't remember. I could do.
Actually, it
We'll
was
do either one.
Jump and Link.
Oh, ours was jumping link. Okay, cool.
Yeah.
So it's similar. So the write back is going to get PC. So WB select is going to be 2,
Okay.
And then PC is going to end up getting PC plus the immediate. So it's going to get the ALU option. So PC
Cool.
select is 1.
All right.
And then for the A select and B select,
Uh-huh.
it's going to be 1 for the top one because we want the PC, and then 1 for the bottom one as well because we want the immediate.
Okay. Good. What is the immediate
Then,
select?
right. Wait, how do you do that input again? Like, what is the what is like a
So
0 or
recall
1 mean?
the immediate generates a different immediate based on the instruction type. There are 5.
Right. Oh, okay. So it's going to be the, I guess, J
Yeah, you're right.
type.
J type.
Okay. Cool.
Oops, whoa. J type. Okay. Cool.
I think
whoops.
that's more or less everything.
Yeah. Okay. Yeah, that's pretty much it. Yep. That's it.
Cool.
Okay. All right. Now the last one was EUIPC group 5.
Okay, so I think the first we think we should use an immediate generator to generate the
Great.
immediate upper limit, and then we go in there and then we do the ALU select to that, and then we feed it back to the all the ALU PC select.
Yeah,
sorry, add with the
so this goes back here, right? And you
add with 0, right? So the marks above that should be 0, right?
Okay, great. Takes register 1.
Yeah, and then we just like add it back to here, and then we do a PC select, right?
Yes.
So we're gonna select the one with yeah. So it's not gonna be 0, right? We're gonna do ALU here, right? And then we do and then go into PC and then just add the bottom part of the PC ALU, I guess.
The upper mux would be a 1, right? It's adding to the PC, not to the register.
Which one?
Oh, yes, you are correct. You're correct. Yes, it should be coming from the PC.
And in that case, RD would always be set to X0. Is that true?
RD would always be set to X0. AUIPC, no, I don't think. No, actually, RD. RD is actually the destination of what this is, right?
Yeah, but we're not like if you had like the other upper immediate instruction, you would store that into an RD, but AUIPC just adds it to the PC, so it's not really storing into any register.
No, but AUIPC should be storing PC plus upper immediate to RD, right? This is what should happen.
Isn't it just adding it to the PC?
Yes, it's adding from the PC plus immediate. But then the result register.
I see. We're writing a register. We're not changing the PC.
Yeah, you're not changing the PC because you only change the PC if you're doing a jump or a branch.
Okay.
Yeah. Okay. So this is actually a 0.
Sorry, can you like elaborate what is AUIPC instruction?
It stands for add upper immediate to PC to program counter. So you add the upper 20 bits, which is what, 22? Immediate 31, 22 to the PC, and then you write that back to a register, and then you increment the program counter by 4.
Oh, okay. So essentially like records the PC program counter by the immediate value.
That's right. Yes, by the upper 20 bits of the immediate value.
By the upper.
Yeah.
Okay.
Okay. So we're almost out of time. So I just want to recap and make some recommendations for you, right? So again, instructions and formats are very important. You want to be able to construct the instruction binary and understand the basic assembly programs, right? So that's for homework mostly. And then understand why the instructions are encoded the way they are. And by doing that, you can figure out how proposed ISA extensions can be encoded based on what inputs you need, okay? The other part of it is you need to understand the data path and control logic. So exercises for yourself, that would be good, is to write the pseudocode and Verilog of every component in the data path. and then check if the instruction is accounted for. By doing this, you give yourself a bit of a head start on your projects also. Also, do the exercise that we just did with those 5 instructions. And that way you can understand how the data path and control is exercised. And by doing that, again, you can easily see how new extensions, new instructions can be added. So for certain types of instructions, you may need to add boxes, add more ALUs, or other types of instructions may only need to modify what's existing in the control logic, media generation, branch comparator, ALU, etc. Okay.
A question here. So if we do the exercise above, is there a way we can verify that if our data path is right? Or
I mean, without really writing out the whole code for this, not really.
No. I'm saying that if we're doing the same exercise, like, is there a way we can check our data path we draw it's right?
Oh, I don't know if all of the instructions have been highlighted in any resource or another.
Okay.
Yeah.
Some were done in lecture.
Yeah, like
yeah,
some were
but
done in lecture. Yeah.
We do have some, but not all of them, right?
But not all of them. Yeah. Yeah.
Okay.
So I mean, like some of the ones that you guys asked to do were not in lecture, right?
I guess.
Yeah. So I think it'll just be more of make sure that like you highlight it and then you go back and you look at the instruction to see, okay, the instruction is supposed to do this. Do my destination register get the correct thing? Does my PC get the correct thing? Does my memory get the correct thing?
Okay.
And then work backwards from there again.
Okay.
Okay.
I had
yes.
Oh, I was gonna say I had a quick question about studying for the midterm. Is this the kind of class where I don't know, like CS classes where just like grinding out a bunch of past midterms is a useful endeavor, or?
So I will say off the bat that this midterm isn't structured similarly to past midterms. So yeah, it's not like you can study and know that a change of numbers or something will get you there, or change of variables. Yeah.
So
especially some of this RISC-V stuff, you do have to really understand what's happening under the hood.
So what you recommend for studying this midterm?
Like I can't tell you to study less of something, right? Because at the end of the day, we're testing whether or not you understand.
Yeah. So I guess like if we try to do like a lot of past midterm, will you think that would be help? And I think you said that it's probably not right. So what are other recommendations that we can do?
Yeah, so I think that making sure you really get homework 4 down is more important than just working through past midterms.
Okay.
Or RISC-V specifically. Yeah. Or some of the other stuff, like logic and cardinal maps and Verilog, those are more universal.
Okay.
So where can I access the past midterms materials?
There's a link on the website with a folder.
In the course website?
Yes.
Yeah, I think there is one. So I just checked the other day.
Yep.
Thank you.
Okay.
Cool.
So I think the midterms will mostly focus on the logic things and also the RISC-V, like data path and instructions.
Yeah, but that covers all of the lectures up until now, right?
Okay.
Yeah.
Thank you.
Okay.
Thanks.
Yep, you're welcome.